This really should have been on the previous board, but I'll tell you now. So if A is n by n and B is n by k, let's say. So if these are my dimensions, then how do I know how big the new matrix when I multiply them will be? Like, how do I know how big the multiplication, the result of the multiplication will be? Well, the dimension of the result will be the following. A times B will be a, basically you just ignore these numbers, the n, the numbers that are the same, just ignore them, and it'll be an n by k. It'll be an n by k matrix. So the size of your result is n by k, where n is the number of rows of the first guy, and k is the number of columns of the second guy. For this to be defined, these have to be the same. The size of the result is just ignore those and take these two numbers, basically. Okay. So how big is this result? Well, I have 2 by 3 and a 3 by 2, so that tells me that my result is going to be a 2 by 2. This will be a 2 by 2 matrix down here. So I know I'm looking for a 2 by 2. So now I'm just going to ask, what goes in the first row, first column? What goes in first row, first column? Well, that tells me take first row times first column. And to do row times column, again, I just do 1 times 1 plus 0 times -2 plus -3 times 3. So 1 times 1 is 1, 0 times -2 is 0, -3 times 3 is -9. So that sounds like 1 plus -9, that's -8. Here's my first guy. Up next, I'm going to take this first row. You know, this is first row, second column over here. So with this, it's going to be take first row times second column. So it's 1 times 2 is 2, 0 times -1 is 0, -3 times 0 is 0, so it looks like it's just 2. Okay. Then I move on. The second row, first column is oh, this was working a second ago. Oh, all right. That marker died on me. How about this? We're going to take the second row times the first column, because I want second row, first column. So what does that give me? 4 times 1 is 4, -2 times 2 is -4, and -5 times 3 is -15. So if I add those up, I should just get -15. And then lastly, second row, second column says take the second row times the second column. I get 8 minus 2 plus 0. So that's going to be 6. So here's my new matrix. Okay. Cool. So there's a couple examples of matrix multiplication. So I don't know. I think what I'm going to do next is talk about a couple special properties of matrix multiplication, and then we'll see where we're at. Yeah, we'll see where we're at. Okay. So just remember, when I multiply A times B, rows of things on the left times columns of things on the right. That's what I want. Okay. Cool. So there are some special matrices I should tell you about that are going to play important roles for us. One of them more so than another, but I'll tell you about both of these. You know, so back in the number land, back when we were doing equations with just numbers and variables, there may be two special numbers that we like. There's 0 and there's 1. And so there are analogs to those for matrices. There's like a 0 matrix, and there's something that's called the identity matrix. And I want to tell you about those because they're going to be very important for us, especially the identity matrix. So I just want to tell you about how those work. So let's talk about the 0 matrix first. 0 matrix is a matrix with all entries 0. So a 0 matrix is just a matrix that has nothing but zeros in it. So of course, I could just draw a matrix of a bunch of zeros. That's a zero matrix. Usually I'm going to talk about n by n. Usually it'll be like an n by n. So there'll be the same number of rows as there are columns for it. Maybe that's something I might call a square matrix because the number of rows is the same as the number of columns. So when I draw the matrix, it kind of looks like a square, right? So here's like a 3 by 3 zero matrix. All the entries are zero. Sometimes I will denote it by, confusingly, I'll just write a big zero, right? So sometimes I'll just write it as a big zero for the zero matrix, and it's up to you from context to know that it means the zero matrix. So like if you see in an equation, I always use capital letters for matrices. So if I saw it in an equation like this, what this means is that the matrix A plus the matrix B equals the zero matrix. That's what I mean. So that's just how something I might write every once in a while. Okay. So that's the zero matrix. It's a matrix that's just full of zeros. The size of it would just sort of depend on the size of the matrices that we're dealing with here. Hopefully, most of the time, it'll probably be a square one. And so what properties does this matrix have? Well, we hope that it has properties a lot like the number zero, and it turns out it does for the most part. So here are some properties of the zero matrix. I'm not going to like prove these to you, but maybe you should think about why they're true. It'll have to do with the fact that zero has these same properties. So here are two properties of the zero matrix, which are really important. So for any matrix A plus the zero matrix is A. And the other way around too, if I do 0 plus A. But I guess I'll leave it up here. So the point is, if I add the zero matrix to another matrix, it doesn't change anything. Notice I'm adding. This is addition, like we talked about yesterday. And another important property would be that so long as this is defined, of course, A times the zero matrix is the zero matrix, and zero times the zero matrix times A is also the zero matrix. So if I'm multiplying by a matrix that has all zeros in it, then I'm going to get a matrix that has all zeros in it. Wherever this makes sense. So whenever defined. Meaning that as long as the dimensions of the matrices make sense, then these are true. So just bear in mind, if you're trying to solve an equation and you end up multiplying something by zero, then you'll just get a zero matrix out of it. Okay. So I think for our purposes, the zero matrix is maybe a little less useful, but it might come up in some problems or something. So I wanted to make sure you guys see that. And then, yeah, just note, compare these to properties of the number zero. Adding a number zero to a number doesn't change anything, and multiplying by zero makes zero. The same properties transfer over to matrices. Okay. The next special matrix is called the identity matrix, and this is going to take over the role of the number one. So this is the identity matrix. And I need to describe for you what it is, how to write it down. It's not a matrix whose entries are all one. It's different because of the way matrix multiplication works. So we're always going to denote it by I, first of all. So I is for identity matrix. And here's how it goes. It is an n by n matrix. So it's a square matrix, and it has the same number of rows as it does columns. And the n can change depending on what the context of the problem is. So if I'm dealing with matrices with 3 rows and 3 columns, then my identity matrix will also have 3 rows and 3 columns. So just bear that in mind. So in reality, it's not one matrix. It's actually a whole bunch of matrices. Anyway, let's not get more confusing than that. let's say it's going to be an n by n matrix, and here are its entries. I'm going to write it in words, and then I'll just give you a bunch of examples to hopefully make it more clear. With ones on the diagonal. So the diagonal, I just mean start in the first row, first column, that upper left corner entry, and go down to the right diagonally. All of those numbers should just be ones, and then 0 everywhere else. So all the entries are either 1 or 0, and the ones are all just in a diagonal strip of the matrix, and everything else is a 0. So let me just give you examples of what I mean explicitly. So in the case of like a 2 by 2, the identity matrix is going to look like this. 1, 0, 0, 1. That's the 2 by 2 identity matrix. Here's the 3 by 3 identity matrix. 1, 1, 1, 0, 0, 0, 0, 0, 0. This guy here. Again, one's going down diagonally like this, and then everything else is 0. Maybe for fun, one more. I'll do the 4 by 4. And I'm not going to do any more because I'll run out of room. All right, there's the 4 by 4 identity matrix. Just so you see what these look like. Again, one's going down the diagonal, everything else is 0. Okay. So this identity matrix is going to be super duper important for us moving forward. It's, next time I hope to start talking about division for matrices, and that won't even make sense if I don't have this identity matrix, and I'll explain why tomorrow. But so we need to know what this is, and now I just want to tell you some properties of it. I'll leave these examples down here maybe, just so we remember what it looks like for some certain dimensions. So properties of I. Really, all I want to tell you about the I is the following. It takes the role of the number 1, and as we know, the number 1, if I multiply 1 by any number, I just get that number back, right? 1 times 2 is 2. 1 times x is x. Right? So multiplying by 1 doesn't change anything. Turns out, same thing is true for this matrix. Any matrix times I just get that matrix back. So in particular, I'll write this way. For any matrix A, for any n by n matrix, A at least, we get the following. A times I equals A. And I times A equals A. So multiplying by I doesn't change anything, so long as that multiplication makes sense, right? So let's just ask maybe that A is a square matrix. So wherever multiplying by the identity matrix makes sense, it doesn't change anything. Okay. X is an identity. So basically, it's like the number 1. So that's basically our main property for this. Again, it's going to be the thing that makes us be able to kind of do division, but we won't get into that today.
Quick question.
Yes.
So when you say A and when you say N, what are you referring to specifically?
So A is a matrix. Yeah. A is a matrix. And when I say N, I'm just talking, so N is, I'm saying that A is an n by n matrix. So that just means n is how many rows and columns it has. This is the number of rows, this is the number of columns. By saying n by n, I'm saying that A has the same number of rows as it does columns. So like, here are some examples of n by n things, right? 3 by 3 means it has 3 rows, 3 columns. That's what I'm referring to.
Gotcha.
And A is just any matrix that has that same number of rows as columns.